Good afternoon, everyone. Today we are going to introduce a brand new unit. We're going to start talking about forces. And really, with forces, what I look at, the main theme of forces is what causes a change in motion. So, what is a change in motion? When your motion is changing, so when your velocity is changing, maybe it's changing from 0 to 100, maybe it's changing from 10 to 25. Whenever that velocity is changing, what causes that velocity to change? And that's what we're going to be looking at in this unit when we look at forces. So, what is dynamics? Another term for this unit is dynamics. So, what is dynamics? Dynamics is the study of forces that cause objects and systems to move. A force is going to be a push or a pull. So we're going to be looking at forces. Forces are going to be a push or a pull. Now, is force a vector? Well, definitely. Force, your direction and your magnitude of your force definitely matter. Okay. Now, what is a force? A force is the ability to cause a change in the state of motion of an object. The ability to cause a change in the state of motion of an object. So when we're looking at objects versus systems, we're going to we can look at this object. The object is, the bike rider, or a scene. We're looking at the road or whatever. So what are we going to do? We're going to have to identify a system. So a system is an object or a collection of objects. Objects are treated as having no internal structure. So when we're looking at this, a system is has properties that are determined by the properties and the interactions of the different structures. Okay, so a system in this case, and in AP Physics, we are working with systems. So we could identify a system in this image. Maybe we could look at the pedals, okay, and how the pedals are working. So that could be our system. Or maybe our system could be the interaction between the wheel, the tire, and the road. Okay. So in AP Physics, we are looking at those systems. We are observing those systems. Okay. Now, we're going to look at force. And what is force? Well, we're going to look at Newton's laws, but the most important thing, force is your mass times your acceleration. Okay. So when a force is calculated, you calculate that by multiplying the mass of an object times the acceleration. So if you think about that, mass is in kilograms, acceleration is in meters per second squared. And so kilograms times meters per second squared is what we're going to be looking at. Now, what is mass? Mass is an object's ability to resist acceleration. So mass is a measure of what we call inertia. Inertia is an object's resistance to change in motion. Okay. So when we're looking at a force that we all know and we all have experience with, we can think about gravity. Okay, that's something that we would think about. But now the most important thing for us to realize is, so we've got fields. Okay, massive objects cause gravitational forces. Okay, and the gravitational force of the Earth on an object is called weight. When the only force is gravity, the object is in free fall. And that's because there's a field acting around it. Okay. There's a force field acting around it. And that force field is dependent on the mass of the objects that are interacting with each other and the distance between those two objects. Okay. But then we also have other types of forces. We have contact forces. And so we're going to look at both of those. So say we're looking at a rocket orbiting the Earth. What is the force of gravity? What's the force of gravity, and what's the direction of that force? So when I look at that, okay, I have my Earth, okay, and I have my object that's rotating around the Earth, okay, or it's orbiting around the Earth. Now, what does that look like? Well, the force field, the force of gravity, the interaction between that object and the Earth is pointed directly down towards the center of the Earth. Okay. And that is the direction of gravity in this case. Okay, so there are some main forces that I want you to be aware of. The main forces that you really need to be aware of are your gravitational force, your frictional force, and your normal force. So, what are all of those? Well, think about yourself sitting on your seat right now. Okay, so you're sitting on your seat. Okay, and there you are, and you're listening to this fantastic lecture. Okay. And what's going to end up happening? Like, what are those forces that are acting on you? Well, first off, we know that force is acting, pulling you down to the ground. Okay. But if gravity was the only force acting on you in this case, then you would be accelerating down towards the center of the earth. And that's obviously not happening. You are sitting still. So there has to be a force that's counterbalancing you, that's balancing out that gravity. And that's called your normal force or the support force. It's the support force from the seat up into your bottom or up onto your bottom. Okay. So you have your gravitational force and your normal force. Normal force is always perpendicular to the surface, always perpendicular to the surface. Force of gravity is always directed towards the center of the earth. Okay. And this is going to be really important when we're looking at things that are on an incline. Okay. And then we also have friction. So we have our frictional force. Frictional force is going to be the force that opposes motion. It prevents an object from moving or slows an object down. So it opposes motion. So it's going to be in the opposite direction of the motion. It prevents that motion. Okay. And then in this diagram right here, so this is your free body diagram. And in this diagram, we also have a force applied. So I could be pushing this box. Okay. In the case of you sitting on your chair, there's no other force. There's no force pushing left or pushing you right or pushing you side to side, right? There's just a force of gravity pulling you down and then the normal force pulling you back up. Okay. So in this case, when we look at these men pulling the rope, what are the forces? Well, you have this. If you're looking at this man right here, you have the force of the man pulling on the rope, and then you have the force of the rope pulling on the man. So that is called your tension, and we can measure that as a T, okay, capital T or an FT. And then in this case, right over here, you have this man is pulling on the rope, and then you have a force of tension going that direction. Okay? So when you're looking at that, if one object exerts a force on a second object, the second object is always going to exert an equal and opposite force on the object. So like I said, we have your man is applying a force on the rope. The rope is applying a force on the man. Man applying a force on a rope. The rope applying the force on the man. Okay? So in this case, we have our ice puck, okay, or our hockey puck. And our hockey puck is sitting on the ice, and our ice rink is at a slope. What are the forces acting on this puck? Well, here's the thing. One thing that you need to realize is you need to realize that you always have your force of gravity and it's always going directed towards the center of the earth. And then you have your support force, which is your normal force, and that's going to be perpendicular to your surface. Okay. Now, in this case, because you have ice, something that's important when you see a question with ice, oftentimes because we're dealing with ice, we're dealing with friction is 0. Okay, so your friction is going to be equal to 0 in this case. Okay, so in this case, you're definitely going to have accelerated motion going down. Okay, unless you have a force being applied up the rink to keep that hockey puck from moving. Okay, now say we have the music department wants to move a piano up a flight of stairs. The movers tie a rope to the piano and pull it up the ramp placed over the stairs. The ramp is very smooth, so no friction. What forces are acting on the piano? Okay, so again, we have our force of gravity is going to go down. We have our normal force, okay? Now, something that's important to note is that I'm drawing my forces from the center of mass, okay? If in a question you're asked to draw from the point of contact that these forces are, because these really are contact forces, then what you would do is you would extend your normal force down here, okay, down to the surface. Your force of gravity is going to act from your center, and then if I had friction, it would act down here at the surface area, okay? But when we draw our free body diagrams, often we radiate everything going out from the center of mass, okay? Also, whenever you're drawing your vectors, the tail starts at that center of mass, and then the head goes out towards the outside of the object, okay? And then there's one other force here. This force is the force of the movers applying a tension. So tension force can be in a rope or a chain, and that's going to be designated as F sub T, or you can just use a capital T, okay? And College Board would know exactly what you were talking about. Any grader is going to know that, okay? Now, in this case, we have a pendulum. Assuming the pendulum in the figure consists of a massive bob hung on a light rope, what forces are acting on the bob? So we're looking at the bob, okay? So can you identify what those forces are? Try to imagine what forces are acting on that bob, okay? So looking at that, what you're going to do is you're going to make sure that you have the force of gravity going straight down. Okay, the force of gravity is going to go straight down. Okay, and then there's not a surface. So a lot of students in this case would say, oh, well, you've got a normal force. You don't have a normal force. You're not going to call that normal force. This one you're going to call tension, okay, because it's a rope. But again, do not identify that as a normal force. That's going to be some easy points that you're going to lose right there. If there's no surface that's holding it up, it's not a normal force. It's usually going to be like tension. Like if there's a string holding it up, there's usually going to be tension, or you could also have something like a spring force, okay? And then if we move on to this next question, which I love elevator questions, I think that they're fascinating, okay? What if this little happy face is standing on a scale, okay? What forces are acting in the elevator? Okay. And this is only, so you take the elevator and you're standing on a scale. I'm going to add this. Okay. Because when you're standing on a scale, you get a reading out from the scale. That scale is the supporting force. Okay. It's actually going to be a spring force, but we can call that's going to be your normal force. And then going down is going to be your force of gravity. Now, the normal force is where you actually get the reading on the scale. The reading on the scale is the reading of the normal force, okay? So those were some free body diagrams. So now I want to take a look at Newton's laws, okay? And we're really going to take a look at Newton's first two laws today, and then we'll look at the third law at another date, okay? So when we're looking at Newton's laws, we want to recognize the first law is the law of inertia. The law of inertia says that an object is going to keep doing what it's doing. Objects are inherently lazy. We are inherently lazy. We have matter, we have mass. So mass is a measure of the matter that we have. That mass doesn't want to move unless it's forced to move, right? And if we're moving, like have you ever been in a point where you're like on a good roll? You're on a roll and you're thinking and you're doing your work, or you're moving. And then all of a sudden someone tries to stop you, and it's so frustrating because a force is acting against the motion that you already have, right? Okay. So the law of inertia states that a body at rest is going to stay at rest unless acted on by an outside force. A body in motion is going to stay in motion unless acted on by an outside force. So if you have an object moving at constant velocity, you would need a net external force to cause it to accelerate, cause it to change its velocity. Okay. Bodies are going to keep doing what they are doing because they are too lazy to change what they're doing. So, mass. What is mass? Mass is the property of a body to remain at rest. Another word for mass is inertia. So, we call mass inertia in physics. We call mass matter in chemistry because mass is the measure of the amount of matter in a substance. Okay. And so, the amount of matter causes an object to want to resist change. Okay. So, mass is the property of a body to remain at rest or to remain in motion, and it's called inertia. An object with a small mass will have a smaller amount of inertia than an object with a large mass. Okay. Have you ever tried to move like a humongous stressor as opposed to moving a chair? It's a lot easier to move a small chair than it is to push a humongous stressor across the floor, right? And the reason for that is because you have a larger amount of inertia. So you have a larger amount of resistance to change in motion. So something that's very important for you to recognize is that when we're dealing with mass and weight, mass does not change when you go to another planet. And why is that? It's because the amount of matter you have is not changing. Since the amount of matter you have isn't changing, the mass doesn't change. So your mass here is going to be the same on the moon, is going to be the same on Mars, is going to be the same on the sun. Now, if we apply Newton's first law, how do we apply Newton's first law? Well, I push a chair across the floor. If Newton's first law is true, why does the chair come to a stop? Why does the chair come to a stop? Well, immediately you're probably thinking friction. Yes, friction is what causes the chair to come to a stop because there is a frictional force between the particles of the chair and the particles on the ground in the floor. Okay, there is a frictional force that's causing that chair to go to a stop because the force that I'm applying is no longer being applied. If I push it, as soon as I let go of that object, my applied force is no longer there. As soon as I let go, I no longer have contact. My applied force is not there. But in this case, what causes my chair to go to a stop is friction. So let's look at Newton's second law. Newton's second law, okay, an example I use, force equals mass times acceleration. When you get in trouble, your mom applies a force to you, right? And so what is a change of motion? We know a change of motion is acceleration because when our motion changes, we have to accelerate. We're changing our velocity, okay? And I said that earlier. What causes this change in motion? What causes the change in motion is going to be a net external force. Now, what is a net external force? Well, it's any force that's on the outside acting into a system. Any force acting outside into a system. Okay. Now, here's the thing. If I had two dogs, I had a Chihuahua and I had a Golden Retriever, and I kick both of them. Okay. I kick a Chihuahua and I kick a Golden Retriever. Which one is going to accelerate faster? And everyone says, oh my gosh, what a horrible example. But it makes sense. Think about it. Your Chihuahua is going to accelerate faster. Why? Because it has a smaller mass. So if I have a smaller mass with the same force, I have a higher acceleration. Small mass, high acceleration. Large mass, very small acceleration. Okay. Now, what about another thing? What if I have my daughter who is 6 and she kicks the Golden Retriever and I kick the Golden Retriever? Which one is going to cause a greater acceleration? Well, hopefully I'm going to be able to cause a greater acceleration because I'm going to have a greater force, okay? Or we could just use a soccer ball in that example. If I'm using a soccer ball and she's got a soccer ball, hopefully my soccer ball is going to accelerate more. Why? Because hopefully I'm going to be applying a greater force on that soccer ball, okay? So greater force causes greater acceleration. Smaller force, smaller acceleration. And then again, greater mass, smaller acceleration. Smaller mass, greater acceleration. So mass and acceleration are inversely proportional to each other, and force and acceleration are directly proportional to each other. The units that we use for Newton's second law is called a Newton. Newton's second law, newtons. So 1 Newton is a capital N, and that's the equivalent of, remember we said mass times acceleration is kilograms times meters per second squared. So 1 Newton is the equivalent of 1 kilograms times meters per second squared. And if you're trying to think about it in American units, 1 Newton is about the equivalent of 0.225 pounds. So I've got some practice problems for us to take a look at, okay? These are your in-class practice problems. So what we're going to do is we're going to look at this first one, and it says for a 5 kilogram box on the ground, what net force is required to move the box at a constant acceleration of 4 meters per second squared? So we have 4 meters per second squared. Okay. We have a mass, and we're looking for force. Force equals mass times acceleration, which is going to be 5 kilograms times 4 meters per second squared, which is going to be 20 kilograms times meters per second squared, or 20 newtons. Okay? Now the next one is at a constant velocity of 3 meters per second. Constant velocity. So what's my acceleration at constant velocity? My acceleration at constant velocity is 0. So therefore, that's what these 3 dots mean in a triangle. Therefore, force equals 0, because my mass times acceleration is equal to 0, right? So no acceleration. Does that mean that it's not moving? No, it tells you that it's at a constant velocity. That just means that it's not accelerating. It's not changing velocity. It's going to keep moving at a constant velocity. Looking at our next question, we have a 4 kilogram object is accelerated from rest. So 4 kilogram object is accelerated from rest in a straight line path over a distance of 10 meters by a net force of 20 newtons. How much time, we're looking for time, does the 10 meter motion take? So let's see. We have a force of 20 newtons. And then we have a mass of 4 kilograms. It's accelerated from rest, okay? So we know V initial equals 0 meters per second. And we know that our change in x is equal to 10 meters. So we need to use a couple of equations in this case. We're going to use the fact that force is equal to mass times acceleration. So we're going to figure that acceleration is equal to force divided by mass, which is 20 newtons divided by 4 kilograms. So we end up getting that the acceleration is 5 meters per second squared. And then the question says, how much time does it take the 10 meters motion to take place? Okay, well, let's see. Do we have an equation that brings together V initial, change in x, and acceleration? Okay, we do. We have our change in x equals V initial xt plus 1/2 at squared. Okay, so this becomes 0 because our velocity is 0. So we end up having 2 times change in x divided by acceleration is equal to t squared. Okay, so then if we look at that, we have t is equal to the square root of 2 times 10 divided by 5. So we have 20 divided by 5 is the square root of 4, so it takes 2 seconds. Okay, so what's important for you to see, and this is so common, that anytime that you have an AP Physics question, they're going to do the best that they can to link concepts. So it makes a lot of sense for College Board to link your study in kinematics with your study in mechanics, your study with forces. So your study with motion with your study with forces. So you can't just forget everything that you've learned. And that's why it's so important that we are not spending this time memorizing. We're spending this time learning the concepts of the material. Okay? So this brings us to another concept or another idea, and that's weight. What is weight? Well, weight is going to be your force of gravity on this earth. Okay, or on any planet, or on any celestial body. However, your weight is going to be different on different bodies, and this is why. Because weight is the measure of the force of gravity. So force of gravity is equal to mass times the acceleration due to gravity, which is mass times gravity. And so that's the equivalent of weight. An object's mass is going to stay constant from planet to planet because the amount of matter is not changing. However, your weight is going to be different because your objects are going to fall at a different rate on different planets or on the moon or whatever. Everything is going to accelerate at a different rate. Gravity is not 9.8 meters per second squared on every single object. It's just close to the center of or close to the surface of our Earth, right? So your weight will change from one object to another, or one, planet to another, but your mass does not change. So let's look at a couple of different examples on this. Okay. First, we have a 6 kilogram cement block is sitting at rest on a scale. Find the weight of the cement block and the normal force exerted on the block by the scale. Okay. So what does the scale actually read? Well, the scale is actually reading your normal force, and that's what we talked about earlier. So we have our scale, and we have the force of gravity, which is the weight, and we have our normal force. Okay, so we have a 6 kilogram block sitting at rest. Okay, well, because it's sitting at rest, the sum of the forces is equal to 0. But we can also look at another identification of the sum of forces. The sum of forces takes our normal force and our gravitational force. Okay, so in this case, I am going to set my down as positive and my up as negative. Okay, because remember, it's all arbitrary. So sum of forces is equal to my mass times gravity minus my normal force. So now I have a system of equations. I have this one and I have that one. So 0 is equal to mass times gravity minus our normal force. Okay. Well, we know that the weight of the object, so we could even separate this out, and that's going to be our weight. So the weight of our object is going to be 6 kilograms. Okay. 6 kilograms times 9.8 meters per second squared. So we end up getting 59 newtons. Now, when I go back to my equation, my normal force is equal to my mass times gravity, which is equal to 59 newtons. So in this case, they are both equivalent to each other. So let's look at another question, and this is applying. So we're looking at the application of Newton's second law. A person ties a 12 kilogram object to a string and pulls upward on it. How much upward tension force in the string is required to hold the object at rest? Okay, so I have my object, okay, and I have my mass times gravity, and I have my tension. And over on the side, I'm going to note what my acceleration is because I'm dealing with forces. My acceleration is equal to 0. So my sum of forces is equal to mass times acceleration, which we know is 0 because acceleration is 0. My sum of forces is also equal to If and I can make my down positive or my down negative whatever I want. Okay, let's go with our standard value for right now. I'm going to make up positive and down negative now. So my upward is going to be tension minus mass times gravity. Okay, because tension's in the positive and mass times gravity is in the negative. So because I have a system of equations again here, I have 0 is equal to tension minus mass times gravity. So tension equals mass times gravity. And that is equal to my 12 kilogram object times my 9.8 meters per second squared. And that is going to be equal to 118 newtons. Okay? Now, how would the magnitude of the tension force need to compare to the magnitude of the force of gravity if the object were to speed up while moving upward? Okay, so now we have our object, we have our tension, our free body diagram has not changed. But I'm accelerating upward. Now, acceleration is not a property of, or is not something that you include on your free body diagram. Always make sure that you put it on the side so that a grader does not think that you are including it as a force vector. Okay. Force, your force vector, your net force causes the acceleration, but acceleration is not a force. Acceleration is a cause of a force. Okay. So we know that the sum of our forces is equal to mass times acceleration. We also know that the sum of our forces, if we have up is positive, is tension minus mass times gravity. Okay? So then what are we going to do with that? We're going to set our sum of forces equal to each other. So mass times acceleration is equal to tension minus mass times gravity. And what I'm trying to solve for here is I'm trying to solve for my tension. So looking at this, how do I get tension by itself? Well, going over here, tension is equal to mass times acceleration plus mass times gravity. Or tension is equivalent to the mass times the acceleration plus gravity. Okay? So therefore, our tension needs to increase. Tension needs to increase. Or tension is greater than your force of gravity. Okay? Now, how would the magnitude of the tension need to compare to the magnitude of the force of gravity if the object were to slow down while moving upward? So if it's slowing down, the velocity is up, but remember, if it's slowing down, acceleration is the opposite direction. So tension goes up, mass times gravity goes down, okay? And I know that my acceleration is down. So what I like to do is I like to make my coordinate system the direction of my acceleration. So in this case, I'm going to make my down is positive and my up is negative. So my sum of forces is equal to mass times acceleration. The reason I do that is because this keeps that mass times acceleration a positive number. My sum of forces is also equal to, so let me stop for a second. I always write up Newton's second law because the sum of forces is always equal to mass times acceleration. And then I take my component forces. So my component forces here, my sum of forces here, are going to be mass times gravity minus tension. So I have mass times acceleration equals mass times gravity minus tension. So if I rearrange this equation, I get tension is equal to mass times gravity minus mass times acceleration. So in this case, tension is less than mass times gravity. Okay, hopefully that makes sense. And then our last problem for today, we're looking at a box sitting at rest on the ground. We have a rope tied to the box pulling it to the right, while a frictional force acts to the left because frictional force is opposing the box's motion. So if a 10 Newton tension force is required, so 10 Newton tension force, so we have our force of tension, is required to pull the box at a constant velocity, calculate the frictional force, and then we have frictional force going the opposite way. Okay? And my free body diagram is going to be the same for every single one of these problems. Okay? So I know my sum of forces in this case is equal to mass times acceleration. Because it's at constant velocity, that's equal to 0. My sum of forces is also equal to tension minus my frictional force. Okay? So 0 is equal to tension minus frictional force. And if I rearrange that, my frictional force is equal to my tension, which I know is equal to 10 newtons. Okay? Now, same situation, same scenario. So we're going to be using this free body diagram for all of question number 5. Assuming the same frictional force continues to act on the moving box, how quickly will the box accelerate if the rightward tension force is increased to a 15 Newton force? So we know tension is now equal to 15 newtons, and we know friction is equal to 10 newtons. So we know sum of forces equals mass times acceleration. Sum of forces is equal to tension minus friction. So mass times acceleration is equal to tension minus friction. Okay, so we have acceleration. I'm going to bring this up over here. Acceleration is equal to tension minus friction divided by mass. So we have 15 minus 10 newtons divided by 2 kilograms. Okay, so we get 5 divided by 2. That's going to give us an acceleration of 2.5 meters per second squared. Okay. Please make sure that you get into the habit of boxing your answers. It just makes the grading a lot easier for myself and for graders at the end of the year when you're taking your AP test. Okay. The next question says, assuming the same frictional force continues to act on the box, what rightward tension force must be applied to make it go at an acceleration of 4 meters per second squared? So 4 meters per second squared is what we're given. Tension is our question mark. Friction is 10 newtons. And acceleration is 4 meters per second squared. So since we're using the same system of equations, I'm not going to rewrite it. I'm just going to say mass times acceleration equals tension minus friction. Tension is equal to mass times acceleration plus friction, which is equal to 2 kilograms times 4 meters per second squared plus our frictional force, which is 10 newtons, and that's going to end up giving us 18 newtons is how much force needs to be applied. Okay, and our very last question for the day is assume the same frictional force continues to act on the box moving with a rightward what rightward tension force will cause the box to slow down at a rate of 3 meters per second squared. So my acceleration is actually going to be towards the left because it's slowing down 3 meters per second squared, or it's going to be negative. Okay. So in this case, I have my tension is equal to mass times acceleration plus friction. So my mass is 2 kilograms, but my acceleration is negative 3 meters per second squared plus my 10 newtons. And that's going to end up giving me my answer, which is going to end up giving me 4 newtons. Perfect. So I hope that was helpful. I hope that helps you get through your practice problems today. And then be sure to check back in tomorrow for a new set of lessons. We're going to go through a few more in-class practice problems. Have a great day.